Welcome back. In this video, we're going to introduce the concept of an outer product of vectors and see how that outer product can be used to represent patterns in data. The objectives of this video are to introduce the idea of low-dimensional modeling of data, define the outer product of two vectors, and then use those outer products to model matrices consisting of data. Along the way, we'll introduce the idea of taste profiles for describing ratings matrices. So we'll begin with the data fitting problem. Let's assume we have measured the price of a particular model of vehicle at several times since it was new out to about 10 years. And what we'd like to do is build a model for the price so that we can predict what a fair price is for this vehicle based on the age of the vehicle. We'll assume we're going to estimate the price, P, and the hat is denoting the estimate, as a polynomial function of the time since the vehicle was new. Now we could use other functions like exponential functions or even sinusoids. We'll denote the price at sale I as P hat sub I, and so the label is P hat. If we use a quadratic model, then we can define a feature vector as 1 t sub I squared, and our polynomial model consists of these coefficients, w0, w1, w2. The inner product of the feature vector and the model gives me w0 plus w1 times t sub I plus w2 times t sub I squared. Now we can collect our 20 measured sale prices into a vector and write this as a system of linear equations, where I have this matrix T, whose rows are the feature vector for each sale, and then we have the model parameters in vector W. It's useful to think about this product, this matrix, and this vector in a slightly different form. What we're used to defining matrix vector multiplication in terms of the inner product of each row with the corresponding set of parameters. And in terms of understanding and interpreting this as a model, it's useful to expand this out as the first column times the first parameter plus the second column times the second parameter plus the third column times the third parameter. And so we're writing our model as a weighted combination, the weights are these W0, W1, and W2, of building blocks. So we're going to have a constant building block, a linear building block, this squared or quadratic building block. So we're saying that our prices can be described as this weighted combination, these building blocks, and these vectors we'll later call these bases. We can think of this as that we're describing our vector of prices as a weighted sum of three different vectors containing fundamental shape information. Now let's suppose we choose these parameters to minimize the squared error between our modeled price and the measured price. And we'll talk later on about the method for doing so. You find that you fit the data with this red curve, and it actually looks like it does a reasonable job of predicting the overall trend that is present in the data. Well, if a second order model is good, using a higher order polynomial might be appropriate. Well, here we're modeling the prices using a 10th order polynomial. So we're describing the price as a weighted combination of 10 different building block vectors. So we've got some weight W0 times the 1, 1, 1, 1 vector plus W1 times all the times at which the data was collected, and so on up to W11 times multiplied by the times at which the data was collected raised to the 10th power. Now if we choose these model parameters, again, to try and minimize the squared error between our measured prices and the predicted prices at those times, what we find is this green curve. It turns out that we're actually matching the measured prices much closer, but the behavior is quite strange. In fact, in between different measurements, the price can behave really strange. And you'll notice here that we're predicting that before 40 months, the price of the vehicle is negative. So clearly this is nonsensical. So what's happened is we've fit the data better by using a higher order model. We have more parameters, but the model is less able to generalize. In other words, it's not as well able to predict what would seem to be a reasonable behavior in between time points at which we have measurements. And this illustrates a common issue in machine learning with respect to model order. If we use a very simple model, we may not be able to capture the trends in the data accurately enough. But if we use an overly complex model, then we may be capturing behavior that's not real and it doesn't reflect underlying trends. So we'll later in the course talk about some principled ways for choosing the order of the model. So what have we learned from this particular example? When we compute the product of a matrix and a vector, we think about that computation in terms of the inner products of the rows of T with the column vector W. But when I interpret this as modeling data, it's very useful to think about it slightly differently. Rather than considering the rows of T, we're going to think about the columns of T, and what this describes is modeling the data as a weighted combination of the columns of T, which we'll call bases. And then depending on the number of terms we include, we have different model orders, and that will trade off our ability to fit the measured data against the ability to generalize. So if we have this case like we did with the 10th order polynomial in the previous slide, where we are overfitting the data, actually trying to model subtle variations that are likely due to noise and other effects, not actual trends that are present in the data. So in this first example, we looked at modeling a vector that is the price data. Well, what if we try to model a matrix? And to illustrate this, I'm going to talk about movie ratings. So we have 4 viewers, Noah, Emily, Emma, and Liam, and there's 4 different movies we're considering here. The Last Jedi, Star Trek, When Harry Met Sally, and Groundhog Day. So we've got 2 sci-fi movies and then 2 romantic comedies. And each viewer rated these movies on a scale of -5, meaning they didn't really like it, to +5, meaning they really enjoyed the movie a lot, it was their favorite. Liam actually didn't get to rate When Harry Met Sally. So this is a classic kind of problem that companies like Netflix or Amazon, other content providers would like to solve, and that can I predict whether Liam is going to like When Harry Met Sally or not. A common way to approach this sort of problem is to introduce the idea of a taste profile that we use to model the preferences of the users. I'm going to assume that our viewers might have a preference for sci-fi movies or a preference for romantic comedies. And so we'll introduce this taste profile, which has opposite signs. So let's use this taste profile to approximate Noah's preferences. Well, it turns out that the best fit to Noah's actual ratings using this taste profile are to assign -3s to the 2 sci-fi movies and +3 to the 2 romantic comedies. So in this case, the weight applied to the taste profile is -3. And this weight, in a sense, tells us how much differentiation Noah made between science fiction movies and romantic comedies. It also tells us the fact that this is negative is that he prefers romantic comedies over sci-fi movies because the negative sign in the 3 makes the ratings go down for the 2 sci-fi movies, but they're in the positive range for the romantic comedies. On the other hand, we can take Emily, a weight of +3 times this same taste profile will approximate her ratings. So 3 and 3, we capture both of those, and then the -2 and -4 for the 2 romantic comedies gets approximated as -3s. So you can repeat this process, and we can approximate our ratings matrix as I've shown here, where we've got Noah's approximate ratings, Emily's approximate ratings, and then Emma, it turns out the weight associated with the taste profile for her would be -1. And so there's not a great difference in her case between preferences for sci-fi and romantic comedies. And then finally, Liam, we can use the measurements we have to identify what the weight should be and then interpolate or predict the rating associated with the romantic comedy. So I've shown that here in red. Even though Liam didn't get to rate When Harry Met Sally, from the other ratings that Liam gave, we can infer that Liam prefers science fiction movies over romantic comedies, and that looking again at this range of ratings here, 3 appears to be the distance or the weight that's associated with this profile to give a good approximation. How we're choosing these weights, again, is a topic that we can talk about in more detail later. As we've modeled this ratings matrix, we're calling that R hat, as an outer product. Okay? It's a column vector T1 times a row vector of weights, which we're calling S1 transpose. If you multiply a column times a row, you get a matrix because the element in the MN position of the matrix involves the mth row of T1 times the nth column of S1 transpose. So if you multiply this out, I'm going to have 1 times minus 3, that's this element here. Then I have 1 times minus 3, that's this element here. Then for the second user, I have 1 times 3, which gives me this element. And let's pick this last one. That is obtained by minus 1 times 3, so I get minus 3. For this last column here, we have a weight of 3 times 1, and then times 1 again, and then times minus 1 gives me minus 3, and then times minus 1 gives me minus 3 again. We've just used one differentiation between the movies, whether they're sci-fi or romantic comedies, to approximate the ratings. Well, what if we get a little more sophisticated? We know that The Last Jedi and When Harry Met Sally are both Carrie Fisher movies. So what if someone has a preference for Carrie Fisher movies relative to movies that don't have Carrie Fisher in a leading role? So we'll define another taste profile, T2, which will have +1 in the positions corresponding to Carrie Fisher movies and -1 corresponding to the positions that are non-Carrie Fisher movies. So again, if we apply a weight to this, that size of that weight is going to tell us that user's preference with respect to Carrie Fisher being in a movie or not. We can approximate our ratings matrix now as the sum of the sci-fi romantic comedy taste plus the Carrie Fisher, not Carrie Fisher taste. So here we have a sum of two outer products. We have the outer product. This is a column involving T1 times a row involving S1, the weights associated with the first taste, plus a column T2 times a row vector S2 transpose that involves the weights associated with Carrie Fisher taste. You can solve for the weights associated with the Carrie Fisher taste, and you find that the first viewer has a weight of 1, so has some slight preference for Carrie Fisher movies. The second viewer, Emily, has a weight of 1/2, which indicates a fairly minor but slight positive preference for Carrie Fisher. The third viewer, which was Emma, has a -1/2, which indicates a slight bias against Carrie Fisher movies. And then the fourth viewer, using the available ratings, so we only had one Carrie Fisher movie in this mix, but given the ones we had, we could estimate that the weight associated with this taste would be 5/3. And so now we can do a more sophisticated modeling of our ratings matrix. So we have the outer product T1 S1 transpose. This was this term that we derived on the previous page. Now we're going to add another factor to the ratings matrix, which reflects the second taste T2 for Carrie Fisher or non-Carrie Fisher movies. And so we multiplied these weights times the taste vector T2, and that gives us this set of values, the extra effects due to Carrie Fisher, and if we add these to our sci-fi romantic comedy effects, we get a more refined approximation to the original ratings matrix, continue to be able to predict the rating for Liam When Harry Met Sally. So the data for Liam had a 4 and a 1. The Carrie Fisher science fiction movie was rated much higher than the non-Carrie Fisher science fiction movie. So this model is going to predict that the Carrie Fisher romantic comedy would also be rated higher than the non-Carrie Fisher romantic comedy. So another way to write this is in terms of a matrix multiplication. So we put the taste vectors into a matrix on the left. The first column is the first taste. The second column is the second taste. And then we put the weight vectors associated with the first taste in the first row and the weight vector associated with the second taste in the second row. Remember, we talked about multiplying block matrices. This is a case of a block matrix. So the rules apply just as they normally would, and I can think about this as a generalization of a row times a column. So to do matrix multiplication, I'm going to multiply this row times this column, and that would give me the first product of the first element in the row times the first element in the column, or T1 S1 transpose, plus the second column, or the second taste vector, times the second row, which is the second set of weights associated with that taste vector. Okay, so I can think about this as multiplying a matrix here times a matrix on the right, and this is a sum then of outer products. Now in general, I can take an n by k matrix R, an n by L matrix T, and an L by K matrix S, and represent R as T times S. So here my T is going to have capital L columns associated with these different taste vectors, and then I'll have capital L rows in my matrix S, and using the principle of block matrix multiplication, I can find that the product T times S is T1 times S1 transpose plus T2 times S2 transpose, and so on, plus TL times SL transpose. In other words, R is equal to the sum from lowercase l equals 1 to capital L of T sub lowercase l, S sub lowercase l transpose. So each of these matrices in this sum is an outer product and becomes an n by k matrix. T sub L is n by 1, S sub L transpose is 1 by k, so when I multiply an n by 1 times a 1 by k, I get an n by k matrix. So we can talk about representing an arbitrary matrix R as a combination of L of these simple factors of outer products. The bigger that capital L is, in other words, the more terms in this representation, the better we'll be able to describe R, but we run into the same issue that we ran into with the vector case, is that the more complicated model, the model with more terms, may not generalize as well, because it may be fitting variability that has nothing to do with the underlying true trends in the data. Now, taking a matrix R and decomposing it this way is something that we'll talk about later. In other words, how would you find a good T, S, and L? Emphasize in the examples of this video is that when we think of matrix multiplication or matrix vector multiplication, when we're computing that, we do that using inner products. We do the inner product of the rows on the left with the columns on the right. But oftentimes, when we're interpreting the meaning of this representation, it's more useful to use outer products, like in this form that we have here. I can think of R as being a sum of component matrices, each being of a very simple structure.